There might be a hole in the universe that lets you skip millions of light years in a single step. No spaceship, no faster-than-light physics, no journey lasting thousands of years, just a tunnel. But here's the catch. The easiest wormhole to describe would kill you the instant you tried to use it, and the strangest ones might not even lead to another place in space. Some could lead to another time. Some could lead to another universe entirely. And some may exist only as equations, never as anything real. Physicists have seriously proposed 10 different kinds of wormholes. And the deeper we go, the stranger and more dangerous they get. Einstein-Rosen Bridge. This is where the wormhole story begins. In 1935, Albert Einstein and Nathan Rosen discovered a mathematical structure connecting two regions of spacetime. We now call it an Einstein-Rosen Bridge. Imagine folding a sheet of paper so two distant points touch. Normally, traveling between those points means crossing the entire sheet. But if you could punch a tunnel through the fold, the distance between them would suddenly become tiny. That's the basic idea behind a wormhole. Except there's a problem. The original Einstein-Rosen Bridge isn't a cosmic shortcut you can simply fly through. It collapses too quickly. The tunnel pinches shut before anything could safely cross it. So the first wormhole was essentially a mathematical bridge, not a doorway through the universe. But physicists weren't finished. Because if spacetime could create a bridge, what if we could stop it from collapsing? Morris-Thorne Wormhole. In 1988, physicists Michael Morris and Kip Thorne asked exactly that question. They designed a theoretical wormhole that could remain open long enough for a traveler to pass through. Unlike the Einstein-Rosen Bridge, this wormhole has no event horizon blocking the traveler. You could enter one mouth, cross the throat, and emerge from the other side. But keeping the tunnel open requires something extremely strange. Exotic matter, matter that pushes instead of pulls, with negative energy density that breaks the normal rules of gravity. In other words, the universe doesn't naturally want to keep this tunnel open. You would have to fight gravity itself. And even if you could build one, we have never found evidence that a macroscopic traversable wormhole actually exists. But this wasn't the only way to keep a wormhole open. The next idea shrinks the problem down to almost nothing. Thin shell wormhole. What if you didn't need to hold open an entire tunnel of exotic matter? What if you only needed a seam? Picture slicing two separate regions of spacetime, cutting away everything on the inside, and welding the two remaining edges directly together. No long tunnel, no open throat, just a paper-thin boundary where two worlds touch. That's a thin shell wormhole, and it's a clever workaround. Instead of exotic matter filling miles of tunnel, it gets squeezed down into a razor-thin ring at the seam itself. Physicists have built this into ordinary general relativity, and even into modified theories of gravity, trying to make the exotic matter requirement as small as physically possible. Smaller footprint. Same unsolved problem. Nature still hasn't shown us that this material exists anywhere, at any scale. So shrinking the wormhole didn't solve it. The next idea abandons exotic matter almost entirely. Ellis Wormhole. In 1973, Homer Ellis found a remarkable wormhole solution. It has no event horizon. It can be traversable, and its geometry can connect two otherwise separate regions of spacetime. Unlike the classic Einstein-Rosen Bridge, the Ellis Wormhole doesn't rely on a black hole horizon hiding the throat. Think of it as a tunnel whose entrance never closes, with space itself forming the walls. The original solution is associated with an unusual scalar field, and later versions have been studied extensively. Even stranger, the Ellis Wormhole can be generalized. Make the throat rotate, and the geometry becomes much more complicated. Which brings us to the next type, rotating wormhole. A wormhole doesn't necessarily have to sit perfectly still. If the throat rotates, space-time itself can become dragged around it. This is similar to what happens around rotating black holes. The wormhole can develop regions called ergo regions, where space-time is dragged along with the rotating geometry. Some rotating wormhole models can even develop multiple throats and extremely complicated light paths. Imagine flying toward the entrance, only to discover that the tunnel itself is spinning through space-time. But rotation creates another possibility. If one mouth experiences time differently from the other, the wormhole may become something far more dangerous. A time machine. Time Machine Wormhole. Here's where wormholes stop being shortcuts through space and become shortcuts through time. Imagine two wormhole mouths sitting next to each other. Now take one mouth and accelerate it to almost the speed of light. Because of time dilation, less time passes for the moving mouth than for the stationary one. Bring the two mouths back together, and their clocks no longer agree. Step into one mouth, and you could theoretically emerge from the other at a different point in time. You wouldn't be traveling faster than light. You would be exploiting the geometry of space-time itself. But this creates a terrifying problem. What happens to causality if you can travel into your own past? Could you create a paradox? Could you prevent your own existence? Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics may prevent macroscopic time machines from forming, and recent theoretical work continues to investigate instabilities that could obstruct these constructions. So the universe may have a built-in rule. You can bend space-time, but don't break time itself. But some wormholes get even stranger, because what if the entrance isn't a sphere? Ringhole. Now, picture a wormhole that isn't a tunnel at all. It's a ring. Fly toward it, and instead of a circular mouth, you're staring at something closer to a giant cosmic hula hoop hanging an empty space hollow in the middle, with the entire universe visible through the gap. That's a ringhole. Light bends around the ring in ways that never happen around an ordinary sphere, so an observer nearby could see wildly distorted, doubled, or smeared images of whatever lies behind it. It's one of the strangest shapes allowed by the math, and we have never observed one. That brings us to the smallest possible wormholes. Quantum wormhole. Forget a tunnel large enough for a spaceship. At quantum scales, space-time may not even look smooth. Some approaches to quantum gravity suggest that space-time could have an extremely complicated microscopic structure, sometimes described using the idea of tiny wormhole-like connections. These would be unimaginably smaller than atoms. They wouldn't be cosmic highways. You couldn't fly through one, you couldn't send a message through one, and we don't currently have evidence that these microscopic wormholes physically exist. But if space-time really has a quantum structure, the universe at the smallest scales could look nothing like the smooth fabric we see from Earth. And some theories take this idea even further. What if a wormhole doesn't connect two places in our universe? What if it connects two universes? Inter-Universe Wormhole. General relativity allows mathematical solutions where a wormhole can connect separate regions of space-time. Depending on the model, those regions could represent distant locations or entirely separate asymptotic regions that can be interpreted as different universes. Imagine walking through a doorway and discovering that the other side isn't another galaxy. It's another cosmos, a universe with different stars, different galaxies, possibly even different conditions for physics itself. But there is absolutely no observational evidence that such a portal exists. Right now, this remains a mathematical possibility rather than an astronomical discovery. And there is one final type that combines almost everything we've seen: black hole wormhole. Black holes and wormholes are often treated as if they're the same thing. They're not. A black hole is a region of space-time from which nothing can escape once it crosses the event horizon. A traversable wormhole is supposed to provide a path through space-time. But certain mathematical black hole solutions contain structures that resemble bridges between different regions of space-time. The famous Einstein-Rosen Bridge comes from this idea. The problem is that the bridge isn't traversable, crossed, and the geometry closes before you can use it as a shortcut. So the black hole may look like a doorway, but the universe slams that doorway shut almost instantly. And this leaves us with the biggest question. Do wormholes actually exist? Right now, we don't know. We've never observed one. We've never sent anything through one. And we don't know whether nature can produce a stable, macroscopic wormhole at all. Every wormhole we've discussed is based on theoretical physics. Some arise naturally from Einstein's equations. Others require exotic matter. Others depend on modified theories of gravity. And some may exist only at quantum scales. But here's the incredible part. Einstein's theory doesn't simply forbid these structures. It gives us mathematical worlds where space-time can bend so violently that two distant locations can become neighbors. The universe could be filled with ordinary stars, black holes, galaxies, and perhaps, somewhere in the darkness, a tunnel that isn't really a tunnel at all. Because if wormholes are real, the shortest distance between 2 points in the universe might not be a line. It might be a hole through reality itself.